AVL tree is a self-balancing binary search tree in which each node maintains extra information called a balance factor whose value is either -1, 0, or +1. AVL tree got its name after its inventor Georgy Adelsonvelsky and Landis. Balance factor. Balance factor of a node in an AVL tree is the difference between the height of the left subtree and that of the right subtree of that node. Balance factor equals to height of left subtree subtracted by height of right subtree, or height of right subtree subtracted by height of left subtree. The self-balancing property of an AVL tree is maintained by the balance factor. The value of balance factor should always be -1, 0, or +1. This is an example of a balanced AVL tree. Operations on an AVL tree. Various operations that can be performed on an AVL tree are rotating, inserting, and deleting. Rotating the subtrees in an AVL tree. In rotation operation, the positions of the nodes of a subtree are interchanged. There are two types of rotations: left rotate and right rotate. Left rotate. In left rotation, the arrangement of the nodes on the right is transformed into the arrangements on the left node. Algorithm. Let the initial tree be like this. If Y has a left subtree, assign X as the parent of the left subtree of Y. If the parent of X is null, make Y as the root of the tree. Else, if X is the left child of P, make Y as the left child of P. Else, assign Y as the right child of P. Now, make Y as the parent of X. Right rotate. In left rotation, the arrangement of the nodes on the left is transformed into the arrangements on the right node. Let the initial tree be like this. If X has a right subtree, assign Y as the parent of the right subtree of X. If the parent of Y is null, make X as the root of the tree. Else, if Y is the right child of its parent P, make X as the right child of P. Else, assign X as the left child of P. Now, make X as the parent of Y. Left-right and right-left rotate. In left-right rotation, the arrangements are first shifted to the left and then to the right. Do left rotation on XY. Now, do right rotation on YZ. In right-left rotation, the arrangements are first shifted to the right, and then to the left. Do right rotation on XY. Now, do left rotation on ZY. Algorithm to insert a new node. A new node is always inserted as a leaf node with balance factor equal to 0. Let the initial tree be like this. Let the node to be inserted be like this. Go to the appropriate leaf node to insert a new node using the following recursive steps. Compare new key with root key of the current tree. If new key less than root key, call insertion algorithm on the left subtree of the current node until the leaf node is reached. Else if new key greater than root key, call insertion algorithm on the right subtree of current node until the leaf node is reached. Else, return leaf node. Compare leaf key obtained from the above steps with new key. If new key less than leaf key, make new node as the left child of leaf node. Else, make new node as right child of leaf node. Now, update balance factor of the nodes. If the nodes are unbalanced, then rebalance the node. If balance factor greater than 1, it means the height of the left subtree is greater than that of the right subtree. So, do a right rotation or left-right rotation. If new node key less than left child key, do right rotation. Else, do left-right rotation. If balance factor less than -1, it means the height of the right subtree is greater than that of the left subtree. So, do right rotation or right left rotation. If new node key greater than right should key do left rotation. Else, do right left rotation. After the whole process, the final tree looks like this. Algorithm to delete a node. A node is always deleted as a leaf node. After deleting a node, the balance factors of the nodes get changed. In order to rebalance the balance factor, suitable rotations are performed. Locate the node to be deleted. Recursion is used to find the node to be deleted in the code used below. There are 3 cases for deleting a node. If node to be deleted is the leaf node, then remove node to be deleted. If node to be deleted has 1 child, then substitute the contents of node to be deleted with that of the child. Remove the child. If node to be deleted has 2 children, find the in-order successor W of node to be deleted. Substitute the contents of node to be deleted with that of W. Now, remove the leaf node W. Update balance factor of the nodes. Rebalance the tree if the balance factor of any of the nodes is not equal to -1, 0, or 1. If balance factor of current node greater than 1 and if balance factor of left child greater than or equal to 0, do right rotation. Else, do left right rotation. If balance factor of current node less than -1 and if balance factor of right child less than or equal to 0, do left rotation. Else, do right left rotation. After performing all the steps, the final tree looks like this. Complexities of different operations on an AVL tree. Each operation is associated with a logarithmic time complexity, denoted by big O of log n, indicating that the computational effort required for these operations grows logarithmically with the size of the data structure. This implies efficient performance for operations even as the size of the data structure increases. AVL tree applications. For indexing large records in databases. For searching in large databases.